Hello everyone, welcome to the presentation of SepEx, which is a visual analysis approach for class separation measures. My name is Jürgen, and together with Tamara Munzner, I'm at UBC. I have done this work together with Marco Hutter and Michael Sedlmair from the University of Stuttgart and Matthias Zeppelzauer from the University of St. Pölten. Class separation is an important concept in machine learning and in visual analytics. Class separation measures aim at quantifying how well distributions of classes, clusters, or groups in datasets can be separated. We focus on measures that give one value per dataset, which is the causes granularity, allowing for the assessment of measures for hundreds of datasets in one analysis approach. In the example, three scatterplot matrices are showing three 5D datasets with two classes, which are blue and red. These three synthetic datasets differ by the degree of class separation from a total overlap to well separated.
Class separation measures have several applications in machine learning. First, they can be used for the selection of good, that means discriminatory features. With class separation measures, we can determine how well a feature separates two or more classes. A classifier built upon this concept is, for example, the decision tree. A second application is the estimation of clustering performance. The evaluation of clustering methods is difficult since usually no ground truth exists. So given two clusterings, it's difficult to say which one is the better one. Cluster quality measures can help us to answer these questions. Finally, we can use cluster or class separability measures to estimate the complexity of a classification problem. Given the class labels for every instance of a dataset, we can estimate how well the data distributions of the classes separate from each other.
Separation measures are also used in the visualization community. Here, they help us to spot scatter plots that have interesting clustering patterns. This is specifically interesting if we have high-dimensional data. Assume you have only 200 dimensions, then there would be almost 20,000 scatter plots in the scatter plot matrix. This is just too much for a human. But with separation measures, we can filter and rank them to focus on the interesting ones. Of course, we can also use them to evaluate and select between different dimensionality reduction techniques. Many separation measures have been proposed in the past, some based on heuristics, some learned from human perception, and many of them quite useful.
There is not a single best measure that fits all purposes best. So, which measure to choose for a given problem? How can different measures be compared, qualitatively but also quantitatively? How do measures behave for hundreds of datasets? And finally, how does dimensionality reduction affect class separation scores? We present SepEx, an interactive visual analysis tool for identifying and comparing characteristics of class separation measures. SepEx supports the interactive visual analysis of up to 12 class separation measures. Along three tasks, analysts can compare measures for high-dimensional data, dimensionality reduced data, and for both. Finally, SepEx is capable of comparing outputs of measures for hundreds of datasets at the same time.
We have chosen a straightforward proof-of-concept setup in our experiments. We take a 5-dimensional synthetic dataset with two classes as a basis and vary the distances between the classes from completely overlapping to completely separated classes in 100 steps. This simple setup allows us to analyze the behavior of class separation measures in an environment that we can easily understand and control, and that minimizes the influences of uncontrollable biases and factors.
A large set of separation measures has been proposed in the past. They differ by the characteristics they seek to capture. Some focus on local neighborhoods, others use entropy within class and between class distances, or minimum spanning trees. For our experiment, we picked 11 of these measures based on their popularity and diversity. While all of them put out a numeric score, they do that on different scales. In practice, this makes comparing them quite hard, especially if you have more than a few datasets.
Our overall goal is to facilitate the comparison between multiple separation measures and multiple datasets. We further break down this goal into three tasks: comparing multiple measures for multiple multivariate datasets, assessing the consistency between multivariate and 2D datasets, and comparing the measures for different dimensionality reduction methods. The overall system looks as follows. We provide one interface for each task. Task 1 can be seen on the upper left. Task 2 is at the bottom, and Task 3 is on the upper right.
The design target of Task 1 is to provide analysts with an overview to compare the characteristics of up to a dozen separation measures for up to dozens of datasets. Analysts need a means to identify individual characteristics and to compare commonalities and differences across measures. This task is a means to the end of selecting the most applicable measures for a task or removing measures with redundant behavior. The Task 1 interface uses parallel coordinates. There's one axis for each measure, labeled at the top, and one gray polyline for each dataset. This choice means that the active value domain of every measure is normalized in the visual space. Here's how we see 11 measures are made comparable, despite differing considerably in their underlying value domains. Parallel coordinates provide a compact display space. Highlighting datasets close together on one axis lets us see whether their distribution changes on all the other measure axes, even the non-adjacent ones. Horizontal line segments between measure axes show linearly correlated measures, whereas slope segments and crossed lines that show changes in rank indicate disagreement and inconsistencies.
The 100 datasets used in the usage scenario differ in a linear increase of class separation, as it was earlier shown in the dataset animation. We analyze the 11 measures along the axis of the parallel coordinates and identify interesting behaviors. 7 measures assess high separability with high values, like the silhouette measure, hypothesis margin, and done. To ease comparison, we flip the axis of the other measures. The linearity of the control dataset is very well reflected by most measures, including average between. In contrast, Davis-Bowden and some other measures show a nonlinear behavior. Most measures perfectly preserve the order of the controlled dataset, except normalized Hubert. This becomes apparent when we select datasets which do not preserve the order for Hubert. Finally, the value domains of the measure outputs differ considerably. Silhouette is, for example, bound to 0 and 1, whereas other measures are open in one direction, some with a very high value domain, such as Kalinski-Harabras.
The Task 2 interface uses slope charts to show ranks within each measure and rank changes between the measures when run on ND versus 2D data. Again, separation measures are the columns. Each dimensionality reduction method is given a row, so we have a grid of measures versus DRs. For each chart, the left axis has the measure outputs for the ND data, and the right axis shows the measure applied to the dimensionally reduced 2D data. The results can be interpreted similarly as with Task 1, where slopes and crossings indicate inconsistencies between measure scores for ND and 2D. Slope charts are appropriate since our goal is to emphasize rank changes, in contrast to the kind of correlation analysis that is typically enabled by scatterplots.
Again, we use the 11 horizontally aligned measures, the result of 3-dimensionality reductions including PCA, MDS, and TSNE, and those are aligned vertically. Some interesting findings include, for the average between measure, TSNE is inconsistent compared to PCA and MDS as it has larger slopes. The PCA-based output shows an anomaly. After a detailed investigation, we found out that in Vika's PCA implementation, the 2D PCA only returns one principal component at some point, when the remaining variance is reporting 0. For Davis-Bowden and Dunn, TSNE has some rank differences and thus is rather inconsistent. Again, TSNE has more slopes and rank changes than PCA and MDS. Hubert statistics has an interesting diagonal pattern across all 3 DRs. The projections seem to compress its value range, but it remains mostly consistent.
The Task 3 interface uses vertical strip plots to depict the distributions of every measure in full detail without aggregation. The plots are aligned side by side horizontally, with the DR methods nested within each column as shown by the bottom labels. As with the other views, the datasets are gray lines, normalized in the visual space to facilitate comparison. In this view, selections are highlighted by blue triangles on the left side. We chose strip plots as a good way to show distributions through visual density with a consistent look and feel to our other designs. A user control allows switching to box plots as a variant for an aggregated result representation.
For the usage scenario, we do use the box plots on top of the strip plots. Some groups of measures with similar output patterns stand out. Average between and hypothesis margin form one group of similar patterns, average within and ball another one. Also, distance consistency and EMST class separation share similar output patterns. Focusing on the comparison of dimensionality reduction outputs reveals considerable differences as well. An unexpected finding is how strongly measure outputs differ for different DRs, using average between as an example. T/E yields average to high separability. All PCA-based results achieve medium separability. In contrast, average between assesses MDS results hardly separable. Finally, we select the most separated datasets according to the PCA anomaly by using the rectangle selection in the silhouette measure at the upper right. It can be observed how differently these PCA-specific characteristic is reflected across the 11 measures. SepEx is the first interactive analysis tool to support the visual assessment of class separation measures for high-dimensional data, DR-reduced data in 2D, and in both. The latter distinction also resembles the three supported tasks. Currently, up to 12 class separation measures can be analyzed using 3 or more DR methods across hundreds of datasets. SepEx helps to better understand the interaction between separation measures, datasets, and DR methods, and thus helps the deeper understanding of separation measures. Finally, SepEx eases the informed selection of measures for downstream tasks such as data studies or sensitivity analysis. Open topics and future work ideas are as follows. For one, algorithmic scalability is an issue. We make use of pre-calculation, especially due to the large number of DR results that have to be pre-calculated. Pre-processing of measure outputs is a different aspect, regarding the inversion of value domains, coping with outliers, and normalizations to cope with the special value domains of measures. A VA-driven aspect regards parameters of DRs and DR variants. An interesting variant of the approach may be to put a stronger focus on the rank-based comparison of measure outputs. Measure of rank violations may also build the basis for visual guidance towards interesting measures. Closely related is the planned extension of the approach for more complex datasets and the question which observations can be generalized. Finally, dependencies of the measure output on data characteristics form a subject to future work.